Okay, group number 6. I didn't realize that I picked you again. I didn't do that intentionally. I didn't put that much thought into which group to go first, other than I wanted to mix it up, and apparently I didn't mix it up all that well. So don't take it personally. But otherwise, please get started if you can.
Yeah, so we kind of noticed that as well, and we were gonna tell you about it, but we figured it was probably too late and didn't. I don't
Was
know.
not intentional, so don't take it
Okay.
personally. It was an accident.
All right. So let's see here. So this is the breakdown of work. Let's see here, group six over there. Oh yeah, we did a lot of this last night. So I guess next slide. Um, so the vertex shader. So here's our state diagram. So a lot of our instructions, mostly everything except for like multiply, divide, load, um, are all finished in execution, and then we have a write back stage. But those other instructions have to go to a separate state to either like truncate or finish the operation. And you can see that in the state diagram there. Our store operation doesn't need a write back state because it's never writing to the vertex or that V array in vertex shader, so that's all good. So everything else is pretty straightforward. We had a lot of trouble the first time we tried to implement it because we are doing too much stuff in the execute state where it was trying to assign things to the an index of the vertex array for every instruction, which was a lot. That's why we had to add the write back stage because it was causing like all these nets and leaf things and lookup tables, and it was just not good. It didn't fit on our board.
So a lot of teams had a very similar state machine diagram. It should look a lot like your 381. I mean, not necessarily as a heavily pipelined version of this, but I was hoping that teams, as you were working on this, you said was straightforward enough. The special functions can get quite complicated, as many teams saw, but this general flow should have felt fairly familiar, comfortable. It's just an example showing how much harder it is to get this working in practice versus, just a model simulation where you don't really have to check that everything is working at that cycle accurate level. But this should have looked somewhat familiar to teams. At least I was hoping it would.
Yeah, because what we had originally was like in the execute state, we would set the index of the V array to whatever, right? The add, the multiply, the divide, or not, I guess multiply or divide, but like the add, the swizzle, the insert, all that stuff. We did that in the execute state, but in practice or in like theory, that should work. But then obviously when it gets synthesized, it like explodes and all this other logic gets put in there. So that's one problem we faced with that. And then I don't know if the rest of my group is here. They were up late.
It seems like almost
Yeah.
everybody is here. So yeah,
Um.
jump in.
Oh, I guess for like the divider, I couldn't figure out how to hook up your divider, so I just kind of looked one up online, and I don't know. I ended up just like shifting the a value by 16 and then dividing it using Vivato's just normal divider, and then truncating to I don't remember the bits, but truncating some bits. And I don't know if we ever completely tested that or not, but it's a little bit different.
I don't think so. Is Micah
So
here?
I do
yeah,
not think.
I could share a little bit about the driver. So our driver isn't too different from like the one that like was provided in the lab. Um, so we obviously like followed all the instructions and stuff. But we didn't do a whole lot beyond that. Um, the biggest difference was that um, like we had flushed the data cache and the instruction cache using the software. And so we flushed the data cache after GL draw arrays and the instruction cache at the start of GL viewport. So a lot of our time went into trying to get the code base to compile on WSL, and that was that was tough. I ended up giving up and just writing a Python script that would build stuff for us in the RDP.
Okay, so our testing, so we made a TCL script of the what was it? The pass-through shader, which was really handy in finding a few problems with our Vertex shader core. We also had another test bench, which was just just like a single instruction or single test of each instruction just to see if like on the surface these instructions worked. And that I guess was still handy, but not as handy as the other one. And then we figured we might want to test other shader instructions as well, because the pass-through shader doesn't test things like multiply or I think add as well. So there are other function or other instructions that we need to test. So we figured we could make a Python script that would be able to take a SGP, a .sgp file and turn it into a TCL script. So that was handy in testing the vertex shifter shader. And then here are all of our problems. So there are the linker issues, memory leaks about every 5 minutes. So and then there's a meme about Vivado taking all of the memory and then
But did the
crashing a
audio
computer.
play
Uh,
the Zoom call just now? 'Cause that's not
no,
very useful to
we
Vivado.
didn't. I don't think we heard it. No.
Yeah, I guess
Yeah.
my speakers aren't connected. That's too bad. Well, everyone play it
Yeah.
separately on their own time. Okay, it's very catchy.
All right. I think that might. Oh, so yeah, I think this goes over the shader converter. So
Yeah.
this is the Python script for that.
And I think, just talking about, I think every team is needed or is going to need some sort of solution in this space, which, understanding from the shader you input, what assembly comes back out. And for the most part, I haven't seen bugs in the assembly that's generated. It may not be certainly as efficient as it could be, but it doesn't seem to have significant flaws in it that would be cause of things breaking. But being able to simulate those test cases and figure out what has exactly happened when your hardware is running, that's the tough part of this assignment. And so, each team has to still have some sort of solution for this. So you had a nice approach where even just hard coding those instructions is a good place to start. The tool does spit out all the binary, so you could just take all those and just make sure you're updating the read data that's coming back out. That's a perfectly valid way of doing it. But having some way of doing it is really important to successfully test that these things are actually running.
I think Rafael, you want to take this one?
Yeah, I mean, I just had this thought that it'd be nice to have just a GUI on top of the application. And I thought, hey, why not just throw in IMGUI? And well, it would definitely crash unless you have some really ugly code that just checks for the existence of a file currently in your home directory to not transmit any of these SGP things to the board. So I think I'll maybe figure out a better way to do this. And currently it's not really working real great because our rasterizer just takes forever. And so you're kind of bound there on input output. So might not end up working real great in practice, but works really good locally.
I think it's very nice to have that. I mean, I don't quite understand what's happening here. So this is the software application on top.
Yep, it's just a GUI. It's attached to like a color array, like one element of the 3 index array. Then it just changes the color. So it's just a nice GUI.
Okay, so this okay, and then you don't translate any of those calls. Your actual OpenGL code is just doing the red triangle or whatever, and you're changing the vertices based on that. Okay, So the idea that you can turn off and not transmit stuff, I think would be very helpful. I mentioned this in your chat for teams
Yeah.
working on getting more advanced applications working. That there's, as you try to bootstrap it up, getting it all to work at once is very hard. But if you could kind of turn it off and then back on for certain calls, that could be very helpful. So it seems like maybe it was a bit of a hack you said, but you kind of have that working, it sounds like. That it
Yeah.
ignores all this, the GUI stuff, and then only transmits this part of the code.
Yep. So on GUI, you have to just specifically call a backend renderer. So in between that, you can just call some code that disables the driver. I just did it by creating a file in the home directory and then in glx trace, just checking if it exists. It's really horrible, but honestly, it works. So whatever.
Okay, good.
I didn't write this one.
Oh, it's a story slide. Yeah, here are some of the challenges, I guess. Resetting C before each instruction. Oh, that was one of the problems that we found when debugging our code was our intermediate value that we were setting things to in the execute stage, we were never resetting. So it was just always saving previous iterations of C, or I guess the previous iterations of instructions into the V array, which was wrong. So yeah. All
All
right.
right, thanks, team. Appreciate it. I can tell you're tired, so let's tighten this up here for the next teams going on here. Talk about what's different between yours and what others have talked about already, and let me know when to advance to the next slide. And let's make a reasonable timeline of these presentations here. So Team 7, you're up.
All right. So first, our division of labor. This was pretty similar to us for previous labs, with Cameron and I really working on the initial layout, which we'll see in the next slide before throwing it away. Ethan really working on the driver code. And then all of us really had a hand in debugging, especially Cameron and Ethan and Riley. So we actually had a very front heavy work and then took a bit of time off in setting up our design and stuff. We verified that it worked pretty early. Unfortunately, we didn't actually synthesize it, which led to some of the errors that you'll see that we come across later. So you can advance to the next slide. So this was our original design. You can see that we actually had a couple of modules, specifically like the decoder and the ALU, were located outside of the state machine and were just constantly hooked up. Now, we thought this would be faster, and it led to pretty clean code, using more structural VHDL. Unfortunately, if you'd like to click, we had to throw this away. Hey, because of some very, very significant timing issues we ran into in synthesis. You can advance 2 slides down. We ended up completely changing our design last minute, literally last night, and revamped it. So it was all very much wrote code, where what happens is, similar to the other teams, we do all the executions within the execute state, and then we immediately write those back to the register file if it's applicable. So that's for like 90% of the commands, with the exceptions being like in FIFO, out FIFO, and the data memory access commands. So
I don't really see the difference though. I mean, it's what would you describe as the difference? So is it that you just switched to just doing some behavioral code versus structurally? That shouldn't make a difference in performance or anything.
It made a huge performance in like synthesis times, as like kind of what we've seen so far, at least.
So it could be what you're not really showing here. Whereas when you did this in a clocked state machine, you actually are inferring registers after each step. Whereas here, maybe you weren't. But I think if you were to take this and just infer registers in between each stage, you should get it's, there's nothing that makes behavioral more efficient than doing the structural version of the same.
Yeah, theoretically, that's what we thought. But the biggest thing that we were able to find when debugging was like the ALU, which calculates the memory address, was it was trying to synthesize that all into like LD2, and that was causing major timing issues. And so when we first added a register, that helped with some of it, but still the structural design just ended up taking longer.
So a disclaimer, we haven't actually finished a synthesis of this rework yet. It's currently running. We tried last night. We forgot to remove a couple of the files from our vertex shader, and that failed our synthesis. We forgot to remove
report back is in the middle of our presentations here. If you could.
Yeah, it's running op design now. So.
Yeah, that's way quicker than
Yeah, yeah. It's
yeah, it was 8 hours before. Yeah, so for driver changes, there isn't too much different from previous groups. So basically, one of the interesting things we did was we treated matrix 4 as kind of 4 uniform vector calls. So yeah, as you can see by my comment, we're pretty sure it works. It seems like it should work fine when we're laying it out in memory. So that should be okay. And then of course we did all the linkages and all those things. We also did the flushing of the data cache on any uniform updates. So we created a static global variable to kind of keep track if anything is updated. And then if something is updated, we update that in the draw or in the frame synchronization call on that swap buffers call. So that's when we do the data cache. And then we also flush the instruction cache when we do the use program, since that's when we're transmitting everything into the onboard memory. So that was kind of the only difference there.
Hey, so on Friday, I was doing a little simulating and trying to figure out why we're not working entirely correct. And this was one of my favorite bugs, where we put in a thing with multiple done signals and multiple commands in between, and we noticed, okay, we're not getting any output after the first done signal. So I changed it to where the done signal is overwriting itself on accident, and it was X's, but we're now getting 4 times the input. So for some reason, every time the done signal went high, we would just stop. It found out to be something with the M-axis, but we changed a few things. So the actual direct cause is not entirely clear, but.
And this happens a lot in simulation where reset signals, I don't know about done signals, but whether they should truly be synchronous or asynchronous, and whether if you make it perfectly synchronous with the clock, does that actually reflect how your chip or how your core comes out of reset? So it could be something similar to that, or just a bug along the way.
Yeah, and well, that's yeah. I went with quite a few of them. It felt like, but yeah, for testing infrastructure, we also used the Python script that was created, put in MP-3. We used quite a few different tickle scripts. Just a normal pass through, like 4 pass-throughs in a row, like I'm about. Like 1 of every command. So while we were doing quite a few of those, we found quite a few timing secrets as well, which is in the next slide.
Yeah, so we were initially failing timing, not necessarily by a small amount there. The starting kind of zigzagging top to bottom was our progress. So we saw that initial one, thought, wow, failing timing, let's take out our divider and our multiplier and take out the more complex instructions. We had a square root core in there as well. We're like, okay, so we take those things out, and then we get that next one. The worst timing decreased, but our total timing blew up even more. So after talking to Zambrino a little bit after that point, we tried to test just the vertex shader on its own, and we never could figure out how to get the clocks set when you're just synthesizing the vertex shader on its own. So then we had infinite or slack timing.
And if other teams could add in the chat, if you did get that to work, that would be very helpful, because the idea would be that we know you can't do implementation on that IP core by itself. It doesn't really map to the top level FPGA correctly, but you should be able to run synthesis just in the IP cores project and get a decent, not necessarily an accurate estimate, overall accurate, but a decent estimate of how your timing is going to be. So you don't have to do the whole multi-hour run to get the result back out. So if other teams were able to get that flow working, some hints would be appreciated for that.
Yeah, so then we Nolan mentioned it very briefly. We were attempting to, some of our execute stage was implementing in the LD kind of stage in our state machine. So we saw it was kind of the way we were passing through immediate values into our structural code. We were kind of doing that as stage late, which was causing some pretty big timing issues. So we actually straightened that out. And then that's that one on the right side where it drops down to 480. So a huge, huge improvement. Still failing though. So then we talked to Steve here between these two next two. And this was basically just fixing our multiplier was what caused this last jump. So we broke multiplication up into 2 stages. And that got us to reasonable timing. And then when we actually implemented that, it improved from the negative 1.3 down to a half, which we called good enough.
Probably good enough. Yeah,
this is kind of all before the redesign that Nolan was talking about. So that was our last synthesis that we got done kind of before the due date. The redesign, tried to synthesize overnight, hit a failure. We restarted it this morning. It's still going. It's running place design now, so definitely going faster than our 8-hour plus build previously.
Yeah, and in terms of results with this older core, all we really got working was pass through, which we got working fairly early, like last Friday. So as you can see, there's the red triangle from previous labs. So then that flat square there is actually that MVP transform thing going on, just without a transform. So we're looking straight at the cube. And then the thing down in the lower right is actually supposed to be our special application. We made like a drag and drop thing, test uniforms where we could drag the triangle around. But because uniforms weren't working in this iteration, it doesn't actually move. So, and then on the next slide, you can actually see with our final synthesis last night, there's a cube in there somewhere. You just got to look for it. You got to hunt down the cube.
Yeah, but what's going on with
Don't
that?
really
though?
know.
So Nathan and I spent some time yesterday trying to reason about the application, which I didn't put that much thought into in the first place, to be frank. Where you have to actually place or do your model view transformation to guarantee your OpenGL application wouldn't clip away the cube itself. So by default, you should be able to see it. And with perspective, we talked about this a little bit in class, but I kind of just moved past it. There is that division step required to do perspective transformations correctly. And if you don't do it, things will look a little distorted. But they wouldn't look like this due to the lack of division, right? It would be just a little bit, it'd be a little bit, I guess if it's not foreshortened, it would just look a little bit stretched in in the X and Y dimension. So it can't possibly be.
Yeah, it's definitely a core thing. I think we're doing something weird with our multiplier in this iteration of our core, and I'm kind of thinking it's stretching the triangles off the screen and they're wrapping around maybe through memory.
Yeah, it could be. The other thing to try for other teams, if I understand we ran out of bandwidth for this one, and it happens every week, and we just do our best. But you have this MVP transform, which is that matrix vector thing. You don't have to have a cube for that. You can do an MVP transform for your red triangle. You won't see anything if you move it in the Z dimension, right? Which is fine, but you can still use that same MVP transform to do all the scaling and offsetting and translation of it in that 2D space, like we were already doing with those little scalar transformations in the vertex shape shifter application. What I would have wanted teams to do is this second application was just supposed to test that you have the matrix uniforms working correctly. So the fact that you're getting this, if you had time, I would have said, well, let's go back, do an MVP transform on a single triangle again, and then that would give you a better hint, because this is going to be, this is very hard to debug, right? There's not much you can do with this other than say it's cool. If you meant to do it, it looks cool.
It looks like random triangles.
We still really need Steve to go into the lab and clean off the
cigarette
spurious,
burn.
the camera issue on the monitor. Well, okay, so progress, definite progress. Thanks, team. Team number 8, are you here today?
Yes, we are.
Okay.
Yeah, so we're team 8, and yeah, we did things. Each of us did some work on the process or the shader core like you'd expect. So we can, yeah, Aaron did a lot of work with square roots. He'll share more about that. Very standard state machine. It looks a lot like what everybody else did. Nothing too special or unique about it. Just trying to make something simple that works. And then we go on to the next slide. Let's see here. This is a quick slide. So yeah, like everybody else, we had really slow send times, and we weren't quite expecting that, so we didn't plan time for around that. So that was a big mistake on our part, and we've been sort of reorganizing our Git and trying to make that work better with how we work as a team. So we had some issues getting that all organized this week. But yeah.
Because we had like a lot of downtime during like synthesis and implementation, I started trying to implement square root, and I didn't end up getting it working in the end, but I did learn about pretty much every single method there is to learn about calculating, well, approximating square roots. I mean, there's several possible methods. One of the first ones I tried was Taylor series until I realized, oh, it's only accurate like between, if you're trying to take the square root of a value between 0.2 and 5.0, there's a way to scale like inputs, except like the amount of values that the Q1616 can represent is so large that even though I tried scaling it down to that like input range, it just ended up having really horrible accuracy. Like the square root of 10 was in the hundreds, I'm pretty sure, and it should not have been like that. Another option was a lookup table, and that's actually a pretty common solution for a lot of like real life applications where they just pretty much have a lookup table of a lot of square roots, and then you just try to do a Newton-Raphson method to calculate square roots. But I decided not to do the lookup table because I was already afraid that we would miss timing if I did that. I found a really easy method with Heron's method and Chebyshev polynomials. But Heron's method is really inaccurate for floating point arithmetic, and it was pretty bad for our Q1616 arithmetic.
So I have to ask,
And
do you
I
have an
tried
applied math
Chebyshev
background?
as well.
This is the kind of thing I learned as an applied math major back in the day, Chebyshev polynomials and Newton-Raphson and things like that. Because the problem, I mean, these are all fun things to explore and try things out. This is a good 2-month-long project to explore these approaches. Yeah, to write some MATLAB or Python code to understand the accuracy trade-offs, to then influence a hardware implementation based on it. That's the problem, though. To me, that's a fun 2-month individual or small team project. Do you have a background in these methods, or were you just kind of learning as you were going? Or do any of your required classes cover things like Chebyshev polynomials? I wouldn't think so.
I'd say kind of both. I mean, for what, basically last semester I don't remember the title of the class. It was like COM-S 527X. It was for what was it? It's for like high performance computing. And I don't know. I read some paper about something very similar to the Newton-Raphson method, and I just ended up trying to use it to influence an implementation here, but I don't know. I don't know enough about math to really get it working.
That's what I was just wondering, because that to me, my own biases, that sounds like a very, very fun thing to work on, but not with 2 days to go and this assignment where you have all the other things to also work on. As an aside, I'm still trying to determine what class I'm teaching next fall, and one option would be the digital VLSI class. But I'd want to do all these kind of things in that class and not what the current class is, which is, make a ripple carry adder and, very simple stuff. So I'd only take on that class if we could do kind of fun things like that in the class. So if there's a critical mass of people who want to, if this looks like fun, which again, this is still, if your job was to do this and I wanted you to have a project for it, for me, almost all of my code would be in MATLAB, and the VHDL would be kind of the uninteresting part at the very end. Maybe exploring pipelines and things like that as well. But the analysis of the math required, the accuracy trade-offs, the resource and accuracy trade-offs, to me, that's a very fun kind of just standalone project idea, whether it needs to be in a class or not. Anyway, it was a good try.
I also made, I was also the one to make changes to the driver. One of the first things we had to do when kind of like refitting everything with MP2 and MP3 was I had to do what a lot of groups did in the previous lab, which is add the 1 second delay to the every buffer swap. Originally, I was gonna try to write a function for every OpenGL uniform, but after realizing that it wasn't as simple as just calling uniform 1F n amount of times, I decided not to do that and just stick to the required stuff, which is GL uniform 4FE and matrix 4FE. For a while, I was really confused with matrix 4FE, but in the end, I got a pretty good answer after asking in the chat, and that actually ended up influencing how we how we order things in, not order things in memory, but how we started to understand how to access things in memory when we were doing the hardware. Bryce, do you want to talk about this one? Okay.
Sorry, I missed the mute button. Yeah, so I spent a lot of time working on testing. So I wrote test cases and little applications for like simulation applications for each of the instructions. And yeah, we did a much bigger simulation this time around. Last time we were just sort of like we'll try something, try it on the board, see if it works. And it was just sort of panicky. So this time we stopped and simmed and fixed a lot of bugs, and that was really helpful. But it was still a lot of waiting for Vivado, like you'd imagine. Big shout out to Ryan. Your Python stuff was happy. I see you smiling. You saved so many people. So yeah, and yeah, look, there's our triangle. And yeah, the chat last night was fun.
Looks great. It's got that realistic scribble shader applied, which is pretty cool. And we'll have this discussion. Where should we go next, right? So I think only maybe 4 of the teams have this actual shaders working in practice. We at least need to have pass-through shaders working to be able to work on anything next for MP4. So that could be something that we can explore as a class here. But thanks, team. All right, team number. I didn't realize there was this many people online last night. Hopefully had good discussion, commiserating. So I can see all the channels and all the discussion. Okay, this is my own bias as an old man. I wish it wasn't at midnight, the night it was due. I understand you have to kind of space out your other classes and other projects, but if we could find other times in which there's this flurry of activity, I could help when I'm slightly fresher and able to provide well-reasoned advice versus panic mode, which a lot of you fell into. So group number 1, you're up.
All right, we're group number 1. So I think we kind of got dragged into a little bit that as well. We definitely tried to work out ahead, but as you'll see, some of our initial plans definitely kind of got, for lack of a better word, re-implemented not too long before we started getting close to the deadline. I'm sure you can read that quote there underneath Braden. But yeah, you go to the next slide. So this was our what was the semblance of our original design. We originally started off thinking we were going to pipeline the entire thing. Seeing as we were like, okay, well, doing things in behavioral is a little bit easier than doing anything in structural. We probably got about 60%, a little bit over that maybe, of the way through implementing everything in pipeline format until we started getting close to the deadline and realizing that I think just a state machine is gonna be the way to go, just to try to get something working. So So basically, on the left there is our ALU. So I don't know why there's an X there. We ended up using that. So basically, that was just the muxes and using the opcode to just figure out which each instruction is going to be. And so the ALU was able to complete everything in one cycle, except for we had a few timing issues with multiply, just going through a few more lookup tables and muxes. So we ended up just breaking that out into the top level design. And then on the right there is a design for a power core. So calculating powers and whatnot, and how that might look in actual VHDL.
So this was kind of our high-level diagram of how our vertex shader actually worked. So we had a two-stage fetch like many other groups, to account for the potential of a cache miss, and then would decode and execute the instruction. Our execution for just about every instruction took a single clock cycle. For every operation that would take more than one clock cycle, which was our square root unit, our power unit, and our division. Those were kind of splintered off into their own state machines. And then there's essentially two more states to this pipeline to account for that, where the first state would fire it off and the second state would essentially wait for it to finish. Similarly, we had a couple stages for load, also again to handle the possibility of a cache miss. Yeah, we didn't end up needing a write back stage. Our register read was always completed in the decode stage, which meant that we could actually write back in the fetch stage. So we used fetch 1 as our write back. We would essentially set a flag for every operation, and it would write it back at the same time as it began priming began fetching from the cache. So that worked out well.
That's pretty cool approach.
So here are power and square root ideas. So Jacob, worked on the square root, and I spent a good amount last weekend just trying to find a good method to go about doing square root. Newton-Raphson seemed like the best idea, and so I went about trying to implement that. There's the method I put all down there in text and the state machine we use. So we load in, and then we go to loop divide, which we divide our input value by our estimated root, which at start would be equal to our input value. Then we go to loops sub, which we subtract the value we found in the last state from the loop divide from the estimated root again. Then we multiply that by 0.5, and then we check that value against our tolerance, which was at 0.5 just for testing reasons, because this wasn't fully functional yet. But this was the main idea, and once the tolerance was found, then we'd go to write output and then go back to load and wait for the next load in.
So do you have a lookup table for the initial estimated root?
No, I believe that would take too long, and I do believe there's a lot of optimizations I'd probably still look at for square root, but this was the main idea going forward with square root.
It's very appropriate. I think if you look at Newton-Raphson, there's issues with convergence. If your initial estimate is completely off, it'll get stuck in a very long convergence. So that's a pretty common approach I see, where you use a small lookup table. So we know we can't do a full 32-bit lookup table for it, or presumably we can't. But you can look at the most significant bit and have a lookup table based on that for your initial estimate, and then these things converge a lot faster. But this kind of approach should, at least in theory, work. It becomes very hard to test. There's no denying that as well. But it should also be something that, certainly if you're using the same divider you would already have had instantiated for the division operation, should be okay in terms of meeting timing for getting these kind of things to work.
Yeah, and just a quick note too about the power core. That was something else we implemented that was fully functional and tested in simulation. Basically, just how that would work is that you just had, you'd wait for a valid computation. You'd get a base and an exponent, and then you would just have one kind of multiplier, just continually multiplying the next square, so just squaring up the tree, and then you'd have another kind of register just accumulating the values that it needs, right, based on the exponent. It should, in theory, work for fractional and integer positive exponents, although in the end, during the simulation, we just figured it might just be easier to just do positive non-fractional exponents, and just include a couple optimizations for other known ones as well.
So this slide for driver changes. So linking, I think it was pretty straightforward, and this is my attempts here to write these two uniform functions. I kind of jumped in and tried to take care of these driver changes as other things were working, and I can't say we didn't get to fully test these, so we are unsure fully correctly implemented these, but yeah.
Conceptually, at least, these look like these should work. So yeah, right, of course, whether they work in practice or not, every team has to get around to actually testing it. But they were supposed to be doable. So yeah, vector of 4, just send 4 values at incrementing addresses. Where do you calculate your? You just do a copy based on the pointer, right? So because you grab. I gotta think about that a little bit. So this is. If count is greater than 0, write v0 fixed. Do you have more code down here that would do v1, v2, v2?
That out there.
Okay, all right, fine. So there's just more code for it. Gotcha. Because you could also do a single write of the whole matrix at a time or the whole vector at a time, but this would also work perfectly fine.
Gotcha. So here's talk a little about our testing strategy. Our main focus was kind of okay. So testing each individual unit at first, so like our ALU, our power, our control when we had one there with our pipeline. And in addition to that, we were using, thanks to Ryan, his Python script to write up some assembly and then generate some TCL scripts there that we could then plug into simulation and test out.
Ryan's getting all the call outs today.
Yeah, so I guess in the end, we didn't end up getting anything necessarily working on the board. We have, as of this morning, we have a couple bit streams now that we can, try and program and see what we get. But a lot of them are still failing timing. So, we were kind of just taking out some different pieces, but, we're pretty confident that it would hopefully work. But, just with the synthesis times, as you can see there too, at one point, I think we were inferring a divider supposedly in one cycle in our square root core. And so I think we had negative 87 nanoseconds of slack. And so that's when you see that rip up and reroute phase. But actually, I think Vivado actually just gave up after that because, it did rip it up, but then just kept going. So, I think we've got a couple places to continue testing from here, but we never quite actually got everything tested on the actual hardware.
My question was: are these progress bars meaningful at all, or are those just major steep?
Yeah, they're
yeah. It'd be nice if at least you could say, "Well, I'm at 73.5%."
No, because there's like a 33, a 50, a 66, and an 80 something, and each one just represents a stage. And they take
that one did
various
end up
times.
taking 3 hours though. So
yeah. I mean, we had one bit stream that actually was very close. It was like 0.127, I think, nanoseconds of slack, which would have been plenty sufficient to run. For some reason, we never actually ran it. I think we identified, while we were building it, we identified an issue in simulation and we corrected it. So we kind of just scrapped it and moved on. But we definitely had everything tested and working in simulation. So I do feel confident that we would at least get a semblance of functionality were we to deploy.
Well, it'd be good to try that out when you get the chances.
Right.
Because I guess the nice thing about MP-4 is you're still using that vertex shader core in 2 places now. So I'll be interested to see teams who are very, very close, needed one more night of push or one more week of pushing on it, what you're able to accomplish for this. So team 2, you're up. Ryan, I cannot read your lips very well, so we cannot hear you, although I know you're talking. Still talking, finger pointing. 1 second, he's saying.
How about now?
Yes, there we go.
Hey, howdy y'all. This is sorry, I'm loud. This is group 2, or we are group 2. My bad. Comprised of a Christian, Ryan, Daniel, and Maggie. Christian did shader core stuff with time enclosure. He did the complex logic and some driver changes. I implemented the more trivial logic and the slower logic, and I helped on report. We all kind of helped on the report. Daniel handled driver changes and messed with caching. Maggie handled the shader core rough draft with me, as well as testing and report. This dumpster fire was brought to you by late nights of Jackbox
Yeah,
games.
I thought you were going to bring up a sponsor just now. Like, oh, here we're interspersing a sponsor. So NordVPN or something is, brought to you. Okay, just please continue, Ryan.
Yeah. Oh, well, is this Christian
No,
slide?
this is my slide.
Okay.
Okay, so for our vertex shader, we had a case statement in the execution state that would determine what opcode we were using. For load, store, and multiplication, we had multiple different states just to help with data dependency issues. And then we had a write back state as well. All of our instructions worked in simulation, but board never really got working. So
yeah, we had some pretty standard driver changes, nothing really new here. So we just added the SGP functions to GLX trace, added the 2 extra uniform functions, and then we added some config flags. We pretty much mostly just reused the decache control flags from the render output, and then we added some extra ones for iCache. And then I think we flushed iCache in use programs, and then we flushed the decache at the beginning of draw arrays.
I know a lot of teams didn't even really get to the point where you were testing these functions. Base address looks like a pointer, but it's not really. I mean, it's our pointer. It's not a pointer to the compiler. So that plus probably needs to be plus equals 4 because you have to sort of manually update the address. I know that's a very annoying thing, right? When it's a pointer and you do plus, it recognizes the type that you're incrementing, but this is really just an int that we're treating as a pointer because we're using addresses to send to the board. So it's a board pointer, but the math won't automatically update for us. So,
okay.
Yeah. But as with a lot of teams, you didn't really necessarily get a chance.
Yeah, we didn't really get a chance. So.
Alrighty. First off, I'd like to say quick disclaimer. I'm really happy that everybody, or most teams, I think all teams, got some use out of my little Python application thingy. We also got some use out of it. So, we mainly just used, or I mainly just used my Python application. I wrote some SGP assembly, ran the script, got the tickle script, and then just threw it into the simulation framework, ran it, and then checked our output signals. I of course, never got cache interaction functioning properly, and that's I couldn't figure out how to interact with the cache in a way that was kind of meaningful, as in like, hey, I can store data long term, but eventually I'm going to be just pretending to be data coming in, so it's not like we're actually testing storing. But yeah, it was essentially write some assembly, run the Python script, put it into the simulator, and yeah, like Maggie said, everything worked in simulation. It's just when we got outside of simulation, everything kind of just, I don't know, it took a while to get something synthesized on the board correctly.
And there's definitely a lot of different approaches to simulating the cache. Every single team ran into that problem either 2 assignments ago or this week. You have to have a solution for it though. So it's either you simulate the AXI responses and you pretend to be the memory controller. That would be one approach for it. or you initialize the cache as a cache with the contents you expect it to have. You have to have one or the other. And because if you have neither, you're not really testing that your loads and even your instruction fetches are working, and you may have some fundamental flaws in your logic. But if it was an issue with just flushing the cache, that should be pretty fixable, because that flushing mechanism does work as intended. So you should have at least like that static triangle that's not moving because your uniforms aren't getting updated. And I would like all teams to get to that point pretty quickly, and then we can worry about how to best flush the cache, which is hard to do in the test bench.
All right. So as you can see, that was the test application using GL Uniform for FV that Daniel created. We never really got to test that far since we were still trying to just verify that pass-through was working. We see that is our MP2 application, or that's a modified the red triangle at the bottom left that we just made colorful during our debugging state and never changed back. And to the right is that is Shapeshifter, but it's just the fixed image. We never got it. Challenges. Oh boy. First off, don't there's no challenges slide. Don't infer a triple ported memory. We had very good simulation results very early on during this MP. We just didn't have a working bit stream because we inferred triple ported memory, and that was causing our timing to fail severely. And it wasn't until Steven so happily pointed that out that we actually were able to start testing on the board. But unfortunately, by then it was Saturday, last Saturday, so right before it was about to be due. I also want to point out that we keep saying everything works, every instruction works in simulation. There's a huge asterisk to that. I implemented square root using a Cordic IP, and I was going to then use the same Cordic IP to estimate power by estimating the exponential and the natural logarithm. However, we got to a point where we were just ripping stuff out so that we could actually map something to the board. So those are not tested. But yeah,
I understand that. And I was trying to tell people, yeah, get pass-through working, which you do, right? So pass-through is clearly working. This is a shader that's doing it's not doing any real math on it. And then go from there. Confirm that your math is working. The way to confirm that would be to maybe change the shader to instead just multiply by a constant and add a constant. And it's still not moving, but at least it's moved beyond its initial specified set of vertices. And then if you have that, where you have it moved over here and maybe stretched a little bit like here, then you know it's just that cache issue. And maybe we should just be helping each other a little bit more. I mean, teams aren't necessarily sharing, here's exactly how we dealt with the cache issue. To some extent you are, but let's start to help each other a little bit out, more in terms of things like that, because I think there's now 8 slightly different partial solutions for interfacing with the cache. And I don't want us to have to talk about cache again, in 2 weeks. So that would be ideal for me, that we can have those discussions and we can just all get to a point where everyone has this working, because it does look like for your team, a couple things you could test without a new board run, but then adding those hooks would allow you to see what's happening. Yeah. So Nathan, your point is exactly mine. I really wanted to see more of that this semester. Maybe it's because we have our own little siloed channels, and there's a lot of discussion teams are doing in their channels, some more than others, but lots of people are sharing their own internal progress as a team. I really want to, we're not really competing in that sense, right? And so, help each other out. When you learn something, some of you are reporting it now once the assignment's due. But if you see something that team 5 or whatever presents today and you'd like to be able to use it, just ask them. They'll share it with you, I would imagine. And so together we can get to a nice baseline, and it can continue to make progress as we go. Because it's going to split now anyway. In a couple weeks here, teams will be working on their projects and sharing general tips like Vivado tips, and how we got this particular part of the flow to work is a helpful thing still. But certainly for MP4, let's try to be a little bit more collaborative, however we want to do that. And don't be afraid to ask a question. I mean, I can't answer them all, and B, I'm not sitting here doing it at the same time you are. I'm trying to provide advice based on code that you are kind of sharing with me, answering questions you're providing. It's not quite the same as having your peers who are also doing the same exact thing you're working on, being able to help you and answer questions along the way. Let's try to get through team number 3. Matt, by the way, that would also be a fine approach of, to the extent you want to share things. Your Git repos are very hard to get through based on your organizational structure. So you would need both access to the repo and a project manager to walk you through how to actually go through the various branches and merge things together. But just sharing basic ideas, because everybody's getting stuck on the same thing. And I'm very tempted sometimes just to copy paste your questions and our discussions in your group channels to the top level channels. But I don't always feel that comfortable doing it, but just ask. And I think be willing to help each other, and we'll have a lot more early progress, hopefully, on MP4, which is intentionally a little underspecified in terms of what you have to do for MP4. All right, that's enough monologue. Team 3, you're up.
All right, so for Team 3, as usual, Nathan did a lot of the stuff. He worked on the shader core architecture and implementation, along with Justin. Lots of debugging, and he also worked on some simulation and breakpoint infrastructure stuff. Along with Nathan on the shader core architecture, Justin worked on some of the OpenGL driver stuff and debugged. Sava and I worked on the ALU, and then I helped Nathan out with some of the pass-through shader simulation, and also kind of made some of the diagrams this time. And then Sava did the custom shader programs. Yeah. So diagram wise, you can see the 2 state machines. The one in the bottom center is just the overall Vertex shader one. The one on the right is the auto-generated Vertex shader core state machine. There's some interesting routing choices that the program is making for arrows, but essentially we had the diagram isn't the greatest this time around, but just, kind of the basic ALU that lots of other people had. We currently don't have some of the power stuff, even tried to implement that. We were just focusing on some other parts of the assignment. And I think Nathan has some other stuff to say on the Vertex shader diagram.
Sure. I think like the only thing I'd add is like our top level, a description of our top level implementation. I noticed I think is just slightly less behavioral than some of the code I've seen or other ones in the slides, although not everyone's shown their code. So really we just like set it up first. We're going to say, okay, any one like result value could be the result of one of 2 buses being, spliced together for some of these instructions. So essentially our architecture is really just execute into code, and the code will generate both control signals and, I guess data signals that kind of control the source for 2 buses that we called X1 and X0. And then there's just control signals that say where should each of them come from and how do you splice them together to make a result. Now, obviously, is that written to memory? Is that written to a FIFO, et cetera? So that was like our overall architecture.
So yeah, nothing too crazy with the uniforms. We were just basically grabbing one vector at a time. And it's pretty much the same thing for the matrix, except with another for loop around it, and then doing a series of SGP write 32 calls.
Okay, this is me. If you're looking at the slides, we'll see some of the text. So for simulation, which we didn't do that much of until at some point we kind of switched and started using Ryan's script, which was really helpful. We modified it to get some functionality that we needed. It kind of generates instead an instruction file that contains all the instructions, but then it makes the top level simulation entry so I can run in a program execution multiple times with different data and uniform inputs, because we also have this header file where we define some convenient stuff like that memory load. That was just an example of some of the logic in it. We'd simulate the cache essentially by just simulating, replacing like the cache ready, cache done signals with forces and storing TCL variables in an array. They're essentially like a hash map. So it would generate all this, and we were able to actually do like a full simulation of what it would look like to do one frame of shapeshifter or a second frame of it, etc. And on the right was kind of our slightly improved hardware ability with the Vertex shader. At some point, I got really frustrated. In fact, this did help me pinpoint down one of the worst bugs in our thing that was breaking everything. So we added some capabilities of our shader to halt at a breakpoint, which was specified by the driver. Say, hey, I'm at a breakpoint. The driver obviously synchronizes with it and grabs some data over AXI buses, mostly just the result of the current instruction, which could be, you know, the memory result, register result, as well as memory interface data. And then they can also read that manually in the driver. And that's when I realized we were like clobbering our memory. Our memwrite signal was not done correctly, so our memory was getting updated very frequently. It's essentially like a store was occurring several times when it shouldn't have, and it was just causing indeterminate uniform values, variable values, all sorts of stuff.
This is pretty wonderful though. So with regards to a breakpoint,
yeah, and it
it
can
was
be
just like
removed
a
entirely.
instruction. It was like an instruction number. Basically, you would specify that it would break on, or it would break every instruction and wait to be told each instruction to continue.
And in theory, in the driver, you could even step through every instruction by saying, hey, breakpoint here. It waits for you, and you can say, okay, breakpoint +1, breakpoint +2. But that was painful to implement the driver. In fact, I didn't need that. I was more interested in checking certain instructions that I was, you know, able to understand in my head. Okay, what should come out of this instruction, and do I expect it? So that was enough right now. But with simple driver changes, you could actually breakpoint the entire execution.
That's pretty cool. If Justin is expecting to be talking, we can't hear you. So does someone else from the team want to talk about results?
Yeah, maybe Sava.
Oh, I thought
explain
is
your
Sava
program.
not here?
Okay.
I haven't actually seen this program at the top right, so that should be Sava.
If he's here, he's quiet.
Okay.
Okay.
Well, on the left, you can see our shapeshifter. And but one disclaimer, well, we didn't actually implement cache flushing. It was kind of like, oh, we'll do it when we get to it. I'll probably try to fix this sometime this week. Right now, we have memory controlled cache control, like from the driver, and we actually set cacheable to false. So this is actually directly accessing the DMEM. Which, look, the performance is actually surprising.
For a single triangle, yeah, the performance will be roughly the same, right? Yes. Okay. All right.
And then on the right is just a picture of the cube one. But, oh, I was going to mention one thing that's like kind of broken now is our render flushing, which was perfect in MP2. So like now our synchronization, we do see flickering issues. And I think you can see in that video, I can't tell how much of it is the camera, but you see some artifacting from previous triangles as it moves. So one of my theories was maybe the done signal from the cache is just telling you, hey, I'm done with your you can correct me, obviously, I'm done doing your request, but it doesn't actually mean it's been represented in memory. I think maybe I have to wait for like an AXI actually monitor that.
I do see some flickering, but the fact that Group 4 and I were discussing this quite a bit, there's still a clear call in between each frame. So we think it's just the camera, right? That you're seeing 3 triangles.
Yeah, we're pretty sure that it's camera ghosting. Just because when we paused our program, it would always just be one triangle.
Well, okay. Well, I also wonder about how that applies to like within a single triangle. We can see some flicker and some like.
Yeah, it does look like. Well, it's hard to say exactly, right? That's the problem, and we don't have a mechanism to grab video from. It would be hard to do. Grab video from frame buffer. We can only grab a single screen. So this is a little bit unfortunate that we're at a point where we can't entirely trust our eyes with what we're seeing with moving things. We know generally it's correct with what you're showing.
Well, I
here,
can run MP2 code like the red triangle and get it to stop at a state where like the bottom 100 pixels didn't quite finish. You can tell it got stuck. So at this moment, our MP2 cache like syncing is not perfectly working anymore, which is kind of confusing to me because the interfacing with the viewport and everything downstream is exactly the same at the moment in terms of how we use TLAST.
So I was just going to ask, finally, we were talking about this relatively late last night, although not that late compared to some other teams working on this. This is an I can't actually tell, or is this the actual perspective view with some?
That's just the orthographic transformation instead.
Well, I guess because the camera itself has got a perspective view, it's hard to see, right? So
I was
okay.
Not only would it just spread out, but because it might generate perspective values that are like considerably greater than 1, you're going to be multiplying your X and Y scales by just enough to blast it off the screen, make it too zoomed in, is what I was always thinking with the perspective one.
Right. You can specify the amount of perspective, right? So that would be another thing to play with to
Oh,
see
okay.
how much it does the distortion. And it shouldn't have been that much for this, but so there's perspective here because the camera that we're pointing at the screen has perspective. Okay, that makes sense. And does anyone then, if Sava's not here, anyone know about this application? It looks very cool. I can't tell entirely what it's doing.
Yeah.
We'll leave it at
Don't think
that.
we're
Cool
sure,
demo
actually.
He
of.
finished it yesterday.
It looks cool. There you go. All right, cool demo. All right, we have time to get to Team 4, and I would like to. Team 5, you are off the hook for today, but we'll get to you. What the? Okay, thanks, team. You're up.
You're welcome for that. So yeah, we're Team 4. I think we kind of do things a little bit differently when it comes to a lot of teams. We don't directly split things up. Initially we kind of just split up in teams of 2 and work on things together. So we started with like VHDL and the shaders. So Ben and I were on the VHDL side, and then Dawson and AJ were on the shaders. And then we found time to. We were almost always all on at the same time working on it, so syncing up was pretty easy. And then you'll find that one of our themes is, if it works, don't question it.
So I think for our vertex shader, we follow pretty closely to a lot of groups with the pipelining and the state machine here. I think the biggest difference we had is, instead of breaking our bigger functions up into multiple states, we had a blocking signal. So we just sit and execute until a function was done. So for example, multiply would just sit and execute for 5 or 6 states, because we broke multiplying across multiple states too. And I think that's our biggest difference. One thing we did also do though is like shift arithmetic and the division and square root. We didn't need those for the first couple applications, so we didn't even look at them. We focused just purely on pass through at a hardware level. And then once that worked, we started looking at what could possibly be different for other applications. And we think that worked pretty well. Okay.
So for the driver changes, the GL uniform functions, AJ was the one that mainly worked on those. I did the linking with them, and apparently I accidentally missed one, which ended up causing some problems that we had no idea what it was. So we found that yesterday, and then we haven't really tested the uniform matrix yet. So we don't believe that's working yet, sadly, but the GL uniform 4 seems to be working, I believe.
Well, the uniform 1
Oh,
is the one which was given to us.
Yeah.
That's the one we've been focusing really, really hard on to make sure like there's nothing wrong with it. And so we never really had the time to go back and fix 4 and the matrix, because we're all working on like usually one section together. So we would kind of just work on
and what I recommend to teams as you go back and continue to test that part is, you can test the matrix without using that cube flyby application. So what you can do is maybe copy the shapeshifter application and make one that, instead of using these scalar constants with GL uniform 1F to shift and move the thing around, just create a matrix that does the same. And you can do that directly in GLM by setting the values of the matrix, or there's the exact kind of calls to scale and shift and things like that. Even if it's all kind of a 2D view, because we don't have depth really working correctly anyway, that should let you know that, at least separate from everything else, that this stuff is working as intended. And I think teams should be able to give that, once they have the basic scalar stuff working, that should be, I agree, kind of a less critical thing to test, but something you should be able to get working relatively quickly.
So I guess with testing, we used the actual raw SPV to SGP Lua file at first, because this was like really, really early on. And I found a site that lets you look at different types of compilations for the Spear V kind of bytecode. And we would take that and run it through the Lua file, and then I would have the dump binary enabled, and so just copy that hex value and run it through a Python program. And so I kind of semi-automated this whole thing near the end. But then we looked later in the lab and I missed the GLSLC thing. And then Ryan made his program, but we already had that workflow that we made before. So it was like too late. And we kind of just made these really sketchy TCL scripts. But the thing is, they actually work decently well, and we found a lot of bugs with just having in simulation our workflow was just a bit sketchy. So, but I think it worked pretty well in the end.
So some of these are kind of hard to read, but like most of the teams, we had issues cache flushing. I think we maybe took a little bit different of an approach. We don't really know what other teams did, but we decided to just hard reset the cache to flush it. The logic behind that being, it worked the first frame, it will probably work the second frame and every following frame if we just hard reset it. So we just put it back to reset state every single time. I think that got the job done all right.
All right. So I can't actually see Zambrino's screen right now.
Is something wrong with the video on my end here? Okay, you see it now.
Cool. So this is on round. For some reason, you can't see the shader. Oh yeah, okay. You're using an older version of the slides. Can you stop the presentation? Just restart it like real quick on the same frame. Oh, you didn't have to refresh it. It updated. You just had to press present again. Okay, so it should have the shader code, so I can kind of explain what's going on there.
Oh, no, everything's gone.
It will come on the next press. There it is.
Okay.
Okay, so we can see the shader code, right?
This is the updated slide. So there's shader code up here that shows.
Okay, cool. Okay, so we had a lot of fun with that special shader right there. At first we were basically trying to get it all to work at once, and nothing was working. And when we tried one variable at a time, so this was when we weren't receiving the actual uniform values, we would basically be able to send one constant or one uniform at a time, and it would update. And then when we send two or more, it would just break completely. And so we fixed that by linking the fetching the uniform location correctly. But when we got to that state, we were able to do addition, but not multiplication. And so we were like, okay, well, let's rip up the multiplication and put in a constant. And so I was using 0.2 at first, thinking that would be fine. And it was still causing it to completely explode. Like we were making like really, really weird triangles. And so we spent, I don't know, like 5 hours plus in simulation just trying to figure out what's wrong with our multiplication. And then I had the idea, I was like, well, I'm going to go back and just try a few other values. And we tried 2. So we would multiply by 2, and the triangle would scale by a factor of 2. And we're like, well, wait, that means our multiplication is working. So we try 0.2 again, and it would explode. Like that bottom GIF there. It would just completely explode. And then I tried 0.5, and 0.5 worked. And we started to get a little bit confused here. And then we would try 0.25, and 0.25 was fine. And then I was like, well, let's continue the trend and try 0.125. And that was also okay. And so we concluded that as long as our fraction is some power of 2, it seems to work. And the lowest amount of a fraction of 2 we got is on that right terminal, if you can see it. There's it's actually uploading or showing the thing that it's uploading. And so the fraction that or the multiplication we used was like 0.000 FE00. So as long as those last two, or last, I guess, byte was zeroed, the multiplication would go through just fine. And so what I did is I cheated and I wrote a function that would just round it to the nearest 128th, I guess.
Yeah, but that's
And
I want to interrupt you there. So I actually appreciate what you're doing here in trying to test and figure out where the error conditions were happening. But when we're doing this fixed point multiplication, um, that truncation, and you actually show it in your slide. I was actually really stuck on the syntax you used for that slide, but maybe I'm just a little tired. This seems like this is in the wrong order or something. But whether that's the correct syntax or not, that issue with you multiply and you wind up losing the lower order bits of your multiplication. That's going to happen with our fixed point because we're taking these two Q16.16 values and we multiply them and get together. We get the W fix, which is 32.32, and then we shrink it back down to 16.16. It's going to be very easy to have scenarios in which your multiplication underflows, right? And that could have been, when you say exploding, that could have been exactly what maybe was happening for that. Something, I'll let others look at this because I haven't been staring at the VTL like the rest of you have these last 2 weeks. This looks wrong. I'm not calling you guys out, but that looks backwards to me.
Yeah, that's not like that anymore.
Oh, okay, so
that's
that
what
was
it
one of
was
the issues that you
beforehand.
fixed.
Yeah.
Okay.
yeah, that was one of the issues that we fixed. And actually, when we fixed that rounding, that's where that meme on the bottom left came from on the next slide, is we changed the way that worked. And that caused our timing to go to 0. And so we got no slack when we fixed that. And it still behaved exactly the same way. And so we are super unsure as why multiplying. I think what's even weirder is it's not just like 8 bits, it's 9 bits. So if I did 250, like multiply by 256 and divide by 256, that causes it to break. It's only when it's 128 or less of a fraction that it causes it to go through. And
well, I don't
yeah.
know, but I think it has just something to do with underflowing, because we're taking relatively small .x and .y values and multiplying them by relatively small uniform values. And so I think it's just a natural limitation of what we're trying to do, because it's not floats. And so I'd have to think about that if you're truncating properly, or if you're actually truncating more than what you need to be doing in your actual implementation. That could be part of it, right? But
that was actually brought up by somebody else. I want to say Matt or somebody brought it up to us at like 1:30 a.m. last night, and so.
What's going on with this one here? And I know people have to go, so we have to end this here. But what's going on with the
Oh, that's our MP-2 coming back to bite us in the butt.
Okay, so it's just moving nicely. And this one looks pretty good. I don't know. It's still kind of stretching. And you were motivating the rest of the class last night at a very early hour at 6:30, letting them know that this was all doable. Thanks, team. And thanks, everybody. Let's leave things here for today. So let's regroup for MP4 tomorrow. Take a look at the MP4 document. The pre-lab is really about looking through some of the OpenGL documentation. It's more of understanding the scope of what you're going to have to implement for the pre-lab for MP4. It's very clear that many teams are going to have to look back at this vertex shader, do a little bit more debugging in the vertex shader before you can make a lot of progress on MP4. But some of the other aspects of MP4 will be in that render output unit, and you should be able to get that working independent of any of the shading here. We'll leave things here for today. Teams are quite close, but there's just that much more testing I think is going to be needed for you. But we'll leave things here for today, and we will figure out our best path forward. I think MP4 is still going to be doable. We're running out of space on the chip, and we're going to make do with what we can do with regards to fitting things that will be appropriate for your project also on that same chip. Otherwise, I'll see people tomorrow morning, and thanks for presenting today. It was fun. I can feel your exhaustion, and we're doing all right. Let's keep going.